Hi everyone. In today's lesson, section 3.3, increasing, decreasing of first derivative test, we're going to continue our study of functions and learning how to graph them without the aid of a graphing calculator. So in the first part of today's lesson, we're going to learn how to test for increasing and decreasing intervals. So spaces on a graph where it's increasing or where it's decreasing. So let f be a function that is continuous on a closed interval from a to b and differentiable on an open interval from a to b. If the first derivative is greater than 0 for all x in the open interval, then f is increasing. So what that means is that if you have a function and the first derivative is positive, meaning the slope of the tangent line is positive, then the function is increasing on a given interval. If that first derivative is less than 0 for all x within the interval, then f is decreasing. And if the first derivative is equal to 0 for all x in the interval from a to b, then f is constant. Then your function is constant. So imagine if we had a graph of a function, just something like this, and if we can prove, and we're going to do this algebraically at first, if we can prove that the slope of every tangent line is positive, then you can see that the graph is increasing at this point. Then at the peak here, the relative maximum, then the slope goes to 0, so it's constant at that point. And then the tangent line, the slope of the tangent line starts to decrease as we approach that relative minimum. And then at the end, it starts to increase again. So we're going to be looking at a graph or looking at an equation and trying to determine those intervals for where a function is increasing, decreasing, and constant. So here are some guidelines for you. The first thing that you want to do is locate the critical numbers. So we're going to use them to determine the test intervals. Okay, next you're going to determine the sign of the first derivative at one value in each test interval. Okay, and finally, you're going to determine which intervals are increasing and decreasing. Okay, on to our first example. Okay, so we're going to determine where f of x, which is equal to x cubed minus 3 halves x squared, is increasing and decreasing. So again, following our guidelines, our first step is to locate the critical numbers. So again, we do that by taking a look at the first derivative. So we have our first derivative, f prime of x. For this function, it would be 3x squared minus 3 halves times 2 times x. And just clean it up a little bit, simplify it to make it 3x squared minus 3x. Okay, we need to find when that first derivative is equal to 0, so set it equal to 0 and solve for x. And we just need to factor out that 3x, and it leaves us with x minus 1 equals 0. So we have x is equal to 0 and positive 1 for our critical values. So the easiest thing to do is to make a number line. And these critical values are going to divide up the number line into 3 sections. I know it's 3 sections because I have 2 critical values. So if we just put 0 here, and 1 will be to the right of it, this is dividing up our whole graph into 1, 2, 3 parts. Okay, so we're trying to see if the graph is increasing or decreasing to the left of 0 in here. So we're going to test a value in each of these three intervals. Okay, so this is where at the critical values, that's when the first derivative is equal to 0. So so just put an open circle there, because again, that's where the slope of the tangent line is equal to 0, so we'd have a horizontal tangent line at each of those 2 points. So pick a number within each of your intervals. For example, to the right of 1, I could choose positive 2, because that's larger than positive 1. Okay, so find f prime of 2. So I'm going to plug that into your first derivative. So you want to do 3 times 2 squared minus 3 times 2, and do the math out. We'll have 12 minus 6, which is 6, and so that's positive, so it's increasing. So I'm going to come in here and put an arrow up to the right. Okay, so our graph would be increasing to the right of positive 1. Okay, so it's increasing on the interval from 1, this critical value right here, off to positive infinity. Now you saw that I got the actual number right here. I said it was 6 and it was positive 6. You don't have to take it as far as actually getting the value 6. That number isn't important. What's important is the sign. Okay, so it was a plus sign, so that's a good thing. So that tells us that it's increasing. Okay, next I'm going to pick a number in the interval right here between 0 and 1. So I want to try 1/2. And again, we're going to plug it into our first derivative, so f prime of 1/2. So we have 3 times 1/2 squared minus 3 times 1/2. Okay, so again, you could do the math out, and this will be equal to 3/4 minus 3/2. Well, I know that 3/2 is 1.5, and 3/4 obviously is 3/4 or 0.75. So I have 0.75 minus 1.5. So I know that this is going to be negative. Again, I don't need the actual number, okay, the negative 0.75. We just need to know that it's negative. So that means that our function is decreasing on this interval. Okay, so draw an arrow to help you out. It is decreasing, and it's decreasing on the interval from 0 to positive 1. Okay, finally we're going to test a number to the left of 0. And easy one to test would be just -1. So take -1 and plug it into the first derivative. Okay, so I have 3 times -1 squared minus 3 times -1. Well, that's going to give us positive 3 plus 3, which is 6. That's positive. So that means that, once again, our function is going to be increasing on this interval from negative infinity to 0. So negative infinity to 0. I know it looks like an 8 there, but it's negative infinity to 0. It's increasing. Okay, so when you're answering a question like this, you have to, it's going to say, like, find or determine where the function is increasing or decreasing. What we're looking for as an answer are the intervals of increasing and intervals of decreasing. Okay, next we're going to learn about the first derivative test. And the first derivative test is basically going to help us find relative maximums and relative minimums of our graphs. It says, let C be a critical number of a function. So again, critical number is where the first derivative is equal to 0 or where it's undefined. So let C be a critical number of a function f that is continuous on an open interval I containing C. If f is differentiable on the interval, except possibly at point C, then f of C can be classified as follows. So if f prime of x, if your first derivative changes from increasing or from positive to negative at C, so let's say your arrows went up and down, at some value c, then f has a relative maximum at c comma f of c. So I'm just going to say relative max. Okay, because imagine if your graph was increasing and then decreasing. Okay, so we're looking at the slope increasing and now the slope's decreasing. So something had to happen at that point right there, and it would be a relative maximum. Okay, if f prime of x changes from negative or decreasing to positive or increasing at c, then f has a relative minimum at c comma f of c. So relative minimum. If f prime of x doesn't change signs, then c comma f of c is neither. So imagine if we had a graph that was increasing on the left side of an asymptote, but also increasing on the right-hand side of an asymptote. So that would be a case where after we found the critical values, when we did the test intervals, it would have two arrows going up like this when you test it out on the number line. Okay, so we're going to put everything all together now. It says use the first derivative test to determine the relative extrema for each of the following functions. So for that function that we worked with before, f of x is equal to x cubed minus 3 halves x squared. Just a refresher as to what the number line looked like. Okay, so we had critical values at 0 and 1. We tested each of those intervals and we found out to the left of 0 it was increasing or positive. Between 0 and 1 we found that it was decreasing or negative, and this is the first derivative again. And to the right of positive 1 we found that the derivative was positive, so the function would be increasing. Alright, this is a change right here at this point from increasing to decreasing, so something important's happening at that point, and that means that 0, 0, so I know x is equal to 0 and I plug it into my original function to get 0 for y. 0, 0 would be a relative maximum. Okay, we have another change occurring over here in the graph at positive 1. Notice that it's changing from decreasing to increasing. So at positive 1, comma, negative 1 half, because that's what you get for y after you plug 1 into that original equation, we would have a relative minimum. Okay, in our next example, we have to do everything. Okay, we had a shortcut there, number 1, because we had already taken the first derivative, found the critical values, did the test intervals, and found the intervals of increasing and decreasing. Okay, so number 2, we've got to take it all the way from the beginning. So from the beginning, we know that we need the critical values, so we're going to find that first derivative. Easy first derivative here, we've got 4x cubed minus 12x squared plus 8x, and that's it. Okay, set that equal to 0 and then solve for x. So 4x cubed minus 12x squared plus 8x is equal to 0. So you have 4x times x squared minus 3x plus 2 equals 0. And this is going to factor into x minus 2 times x minus 1. And again, this is equal to 0. So 3 critical values. X equals 0, x equals 2, and x is equal to 1. Okay, so next, let's get this up a little bit, and we're going to set up our number line here. And again, we want the critical values to be listed in order, just like you'd see on a number line. Kind of pretend like this is the x-axis. So we have x equals 0, and 1, and positive 2. Okay, you need to test a number in each of these 4 intervals now. Okay, we have an interval from negative infinity to 0, an interval from 0 to 1, an interval from 1 to 2, and then an interval from 2 to infinity. Okay, so for my first check, I'm going to do f prime of, say, negative 1, because that number would be in this first interval. And f prime of negative 1, it's easy to test in this stage right here in its factored form. Like, imagine if I put negative 1 in for x. 4 times negative 1 would make that 4x negative. So just think about the signs here. Don't worry about actually finding a number at the end. We're only concerned about the signs. If I put negative 1 in the next set of parentheses, negative 1 minus 2 would make it a negative. And then finally, the last set of parentheses, negative 1 minus 1 would be negative 2. So we'd be multiplying 3 negatives together, and the end result would be a negative. Okay, so that tells me on this interval the function is decreasing. Okay, in the next interval, I'd probably want to choose 1/2 to test. So we want to find f prime of 1/2. And in a similar way to what we just did up above here, we want to plug 1/2 in for x in each of our 3 spots here. 4 times 1/2 would be positive. Would be positive 2. 1/2 minus 2 would be negative, and 1/2 minus 1 would also be negative. Right. When I multiply all those together, it would end up being a positive. So that tells me that on the interval from 0 to 1, my function is increasing because it's positive. All right, again, need a little more room here. In the next interval, let's test positive, let's say 1.5 or 1.5. Okay, so we want to do f prime of 1.5. So 4 times 1.5 would be positive. 1.5 minus 2 would be negative. 1.5 minus 1 would be positive. So the product of those 3 numbers would end up being a negative, and that means that my function is decreasing on the interval from 1 to 2. Okay. All right, finally, let's test something in this last interval, anything to the right of 2. I might even just put in positive 3, so f prime of 3, test it out. 4 times 3 is positive. 3 minus 2 is 1, so that's positive. And then 3 minus 1 is 2, that's positive. So the product would be a positive number. And that tells me that on this last interval from 2 to positive infinity, the function is increasing because the slope of the tangent line would be positive. Okay, finally we have to determine the relative max and min in here. Okay, there are 2 places where it changes from negative to positive. So if you check that out right here at 0, we're going from decreasing to increasing. And over here at positive 2, we're also going from decreasing to increasing. So we would say that there are 2 relative mins, and they would be at 0. And then you have to plug 0 in for x into your original function, and you would get negative 5 out. And then you have to check out positive 2. Again, plug 2 into the original function, not the first derivative, but the original function, and we get negative 5. And then finally, if you take a look at your graph, I don't know what I was spelling right there. Let's try that again. Relative. And we're looking for a relative max. And that's going to happen here at positive 1 because the function goes from increasing to decreasing. So relative max is going to happen at 1, negative 4. Right. If you're ever asked to give the intervals of increase and decrease, you could say for this particular one, intervals of decrease would be negative infinity to 0, and from 1 to 2. They're open intervals, okay? Increase We have two intervals from 0 to 1 and from 2 to positive infinity. Okay, just so you know, you may be asked to list those intervals where the function is increasing and decreasing. All right, if we take a look at number 3, again, we're looking for relative extrema, so we have to go through the process, find the intervals of increase and decrease based on our critical values, and then once we find where it's increasing and decreasing, we can determine if there are any relative mins or relative maxes. Okay, so the derivative in number 3, we need to use the quotient rule. So g prime of x is equal to low x plus 1 d high, which is 1, minus high d low. And it's all divided by low squared. Okay, so g prime of x will give us x plus 1 minus x, all divided by x plus 1 quantity squared. So our first derivative is just equal to 1 over x plus 1 quantity squared. Okay, so critical value in here, we won't set it equal to 0 and solve because we wouldn't come up with anything. So there's no place where the derivative is equal to 0, but there is a place where it's undefined, and it's undefined at x equals negative 1. So our critical value is negative 1. All right, well, that makes it pretty easy for the graph because we only have two intervals to check. We have from negative infinity to negative 1, and then negative 1 to positive infinity. Okay, so choose a number on either side. To the left over here, I could choose something like negative 2. So let's find f prime of negative 2. Again, we don't need to concern ourselves with finding the actual value, just think about the sign. And that would end up being positive because no matter what you have in the denominator here, it's going to be squared. So whether that number is positive or negative after you square it, it'll end up being positive. So if you come back up to your graph here, this function is going to be increasing on the interval from negative infinity to negative 1. Okay, we're just going to keep this open here. Next, test out a number in the interval to the right of negative 1. So maybe test out 0. That's an easy one to plug in. And we'd have a positive number as well. It would end up being positive 1, actually. So this function is also increasing from negative 1 to positive infinity. Okay, so we could say that f of x is what's called monotonic. In other words, it is strictly increasing. Okay, so there are no relative extrema. And just to explain why, we understand that this graph has an asymptote at x equals negative 1. But it is a rational function, and this is what I was drawing for you earlier. Okay, so it's just going to always be increasing. Okay, on to the last one. Okay, and number 4, we need to find the critical values first. So let's take the first derivative, and we'd end up with 2x, and then it would be minus 2 divided by x cubed. You could rewrite it as plus, like x squared plus x to the negative 2, and then you just take the derivative. So it would end up being 2x minus 2 over x to the third. Okay, let's find the critical values by setting 2x minus 2 over x cubed equal to 0, and then solving. So we'd have 2x is equal to 2 over x to the third. You can cross multiply. We'd have 2x to the fourth equal to 2, or just simply x to the fourth is equal to 1. When you take the fourth root of both sides, because it's an even root, we need to rewrite it as x equals plus or minus 1 in here. Okay, so think about our number line and looking at the signs on the number line. We're going to split up the number line using our critical values of -1 and +1. So let's put -1 to the left and +1 to the right. And again, we also have another critical value, and that's at x equals 0, okay? Because this will be undefined when x is equal to 0, so I need to squeeze that in here. Actually, let me redraw this. Well, maybe not. Let's squeeze 0 in there. So you have -1, 0, and +1 for the critical values. And again, critical values come from the first derivative being equal to 0 or when the first derivative is undefined. Okay, so we're going to test out some numbers here. So we have 4 intervals, so we need to do 4 test values. So you want to take a look at what happens when the first derivative, or at the first derivative of, say, -2. Because -2 would be in this first interval. And when you plug -2 in there, it would actually end up being a negative answer. So it would be 2 times -2, which would make it -4, and then minus 2 over -8, which would end up being +1/4. So you'd have -4 plus 1/4, so it would end up being negative. So on the interval from -infinity to -1, it's decreasing. Okay, next we want to test it out on our next interval between -1 and 0. So I would say try -1/2 and make use of the graphing calculator to help you plug that in. And it turns into a positive number. So it's increasing on the interval from -1 to 0. And the next interval between 0 and 1, I would probably test +1/2 in our derivative and see what happens. And it's going to turn out to be a negative number, so it's decreasing on the interval between 0 and 1. And finally, in the last interval, let's try something to the right of +1. You can keep it simple, try +2. And that's going to turn out to be a positive number after you do the math. So it's increasing on that last interval. Okay. If we take a look in here, it is there's a relative min in 2 different places, right here at -1 and here at +1. So we want to say there's a relative min at -1, 2, and again, to find the y value, just plug your x value into the original function, and the other relative min is at +1, 2. Okay, in this particular case, there's no relative max, so this just goes to show how you have to be careful. It looks like there is a relative max in here, where it's changing from positive to negative. But remember, what's happening at x is equal to 0 is that this function has an asymptote. It's undefined at that point. So there's no relative max. Okay, so if we take a look in tonight's homework, you're doing page 186, number 21, number 30, number 33, just parts A through C only. And then please do number 41. Okay, good luck with your homework as always. We'll go over some questions in class tomorrow, but make sure you do your homework.